Today we are going to bridge Taylor polynomials, Maclauren polynomials with series, and we're going to talk about Taylor and Maclauren series. But before we get started, I have another thing I want to look at, and that is this activity here I call What's the Pattern? Okay? This is going to help you as we do one of the steps in the process today, and that is building your series and seeing what the patterns are. So, if you see the numbers either on top or bottom of a fraction, 7, 11, 15, and 19, what is happening from one term to the next? Adding 4. So what I'm going to do is write down plus 4, and plus 4. Now, if you are adding a constant term every time, that means that in your summation there will be that number times n. Okay? So if I was adding 6, there would be a 6n in there. So if I start at 1, now you can start at 0 or 1. There's a couple of times where it's not good to it matters which one you start at. But in this instance, I'm going to start at 1. You plug in that number and then figure out how many more you would have to go to get to this number. So how much more should I add to this? 3. I should add 3 to this, okay? If I started at 0, I would have 4 times n plus what to get this? 7. If I started at 0, if this was n equals 0, it would be 4n plus 7. That would be the difference in the pattern. So what I'm trying to show you is if your numerators or denominators go by adding every time, your term over here is that number times n plus or minus an amount. Okay? The next one, what's happening here?
Times 4.
This is times 4. Does anybody have a guess as to how that's going to look in the series?
Is it like 4 to the n?
It is 4 to the n. That is correct. Okay? Now, if we start at 0 this time, I would have to do what?
Subtract 1.
I don't want to subtract. I want to multiply by something. I would have to multiply by 3. This right here is a geometric series. Anytime you multiply by the same amount every time, it's a geometric series, and the geometric formula, remember, is the first term times r to the n. Okay? So you would put the first term here, and then the multiplier to the nth power. That's how that works. How would it change if I started at 1? How would it change if I started at 1? It would be n minus 1 up here to create the 0 that I need to make the first 4 go away. Are y'all with me? Okay. Next one. What is happening here? I am adding first 3, then 5, and then 7. Okay? Now, what I want to show you is this. If I do that again between what my adding numbers are, what's the difference here? I'm adding 2 and adding 2. Okay? If it takes you 2 attempts to get to where they're all the same number, that means that your equation is n to that power, n squared. Okay? And here's the reason why. It has to do with derivatives. What power would you have to take the derivative twice on to get a constant? Think about it.
Oh, yeah.
It would be a squared, wouldn't it?
Yeah.
N squared becomes 2n. 2n becomes 2. So you need 2 changes, rates of change, in order to get a constant. So it's n squared. If it took me 3 attempts to get it down to constants, this would be n to the third. So this is like a p series. Okay? These, however, we discovered last class, need to start at 1. They really need to start at 1. So with the first term, what would I be adding to that to get the 3? I would have to add 2. Agreed? Now, does that work for the next one? Is this 2 squared plus 2? Is this 3 squared plus 2? Yes. So this one is always better to go ahead and start at 1. Do you see how that works? So if it's constant, which you can't see off the screen now, if it's constant adding, it's that number times n. It's constant multiplying, it's that number to the n power. If you have to do it twice, it's that n to the power. Now, I'm bringing this one up just because we haven't looked at it in a while. What's happening here? Times 2, times 3, times 4. Do y'all know what that is? That is factorial. That is factorial. That's n factorial. Okay? So, later on in class, if you want to write all this down, I will put it back up here and you can do that. Keep it in your notes. Because today and next class, actually the rest of this week, this is going to come in very handy. Okay? Any questions about this part? Awesome. Now go to your notes page, please. You have, let me turn this over. You have Taylor and Maclauren series up at the top. And we've done Taylor and Maclauren polynomials, yes? And we talked about a review of that yesterday. What I want you to do right now is take your flip book, open it up to the page with both of the things with Taylor and Maclauren. All right? I know the video can't see both of them. And I can't zoom out because it won't let me. But I want you to tell me what is the difference between the two equations on the two cutouts that we put in there, the Taylor polynomial versus the Taylor series. I'll give you just a minute to think about it. Michael, what do you see?
Taylor series show like the sigma and then equals 0.
Yes.
And then the other one shows Pn.
Exactly. That is the big difference right there. Because the Taylor is a series, it has the sigma notation, because that is its notation for a series. There is one other tiny little thing that I'm not sure anybody has noticed at the end of each one. What do you see at the end of the one of them continues on. It has dot, dot, dot. That dot, dot, dot is called an ellipses. Okay? That means it continues on and on and on. That is the big difference mechanically between the two. A Taylor polynomial stops. And they tell you, I want a 3rd degree Taylor, I want a 4th degree Taylor, or whatever. That's why it goes, it does say n, but that n is wherever they want you to stop. The series, however, is infinite, because if you look at the sigma notation on this, if you look at the sigma, it goes from 0 to infinity. It goes on forever. So, other than that, it's pretty much exactly the same thing. The only difference is these are now going on forever. So what we're going to do is we're going to revisit Taylor polynomials, but we're now going to tie in what we did last class, which is the center, the radius, and the interval of convergence that we worked on. Okay? So, let's go to the notes. This top part is a little bit confusing, so I want to jump right to the middle. The power series is a Taylor polynomial is a type of power series, okay? It is taking an e, a sine, a cosine, or a complicated function and turning it into a polynomial. Okay? So, what's happening here, this is this Taylor series and the Maclauren series. It's Taylor series, if c is 0, then it's the same thing, and it's called a Maclauren series. Now, the bottom, this is in your flip chart already. At the bottom, it talks about the steps that you follow. Okay, we're going to do exactly what we used to do on Taylor's. We write f, f prime, f double prime, f triple prime across the top, take those derivatives, plug in the c value, put the factorials underneath them, and then go from there. Now, let's go back up to these two right here. Can you see this? Yes. I want to add in the over 0 factorial right there and over 1 factorial right there. I wish they would leave those on because that, I think, helps you see the pattern. We always put 0 factorial under the first one. Do it on both lines, 0 factorial, 1 factorial, and so on. Okay? We're going to rebuild those terms. We're going to write them all out, and then we're going to look at the numbers to see if we can figure out the pattern based on what we were just doing a few minutes ago on paper. Okay? After we figure out the pattern, we can then find the R, find the interval of convergence like we did last class. That's where we're going with this. Okay? So, there's nothing really else to write on this side. I'm going to go to the back. So everybody flip over on the back. And let's go ahead and do number 1. Okay, it says use the function of f of x equals cosine to find the Maclauren series and interval of convergence. Now what does Maclauren mean that c is? 0. So I'm going to write right here that c equals 0. I'm going to need that later. Now, they put their derivatives in a chart form. I like to write them across the top because then you can just build your fractions from there. But we're going to go ahead and use what they have. So, start with cosine. What is cosine's derivative? Negative sine of x. Let's do all the derivatives. What's the next derivative? Negative cosine. The next derivative? Positive sine. Then cosine. Then negative sine. Now they go out 5 derivatives. There's no set number that you need to go, but you just need to go enough so that you can see the pattern. Once you've got the pattern figured out, you're good. And we'll do a couple practice ones to show you about that. Now we're going to go back and plug in 0 because that's what C is. So when I plug 0 into cosine, what is the cosine of 0? 1. And the negative sign of 0 is 0. What's the next one going to be? Negative 1, then 0. Okay. Now what we're going to do is over to the side, we're going to go ahead and draw our sigma, and we're going to leave some space to write what the pattern is in a minute, and then put the equal sign. I want to copy down what everything's going to be. Okay, remember that these numbers we just generated are our numerators. So it's going to be first a 1 over 0 factorial x to the 0 plus 0 over 1 factorial x to the first, and just continue the pattern. And then negative 1 over 2 factorial x squared, 0 over 3 factorial x to the third, 1 over 4 factorial x to the fourth, 0 over 5 factorial x to the fifth. How do I know? If I just asked you to give me the third derivatives term, how would you know which factorial it is? It'd be x to the third because it's a third derivative, and it'd be a 3 factorial on the bottom. So whatever the derivative number is, remember, that's your factorial number, and that's your x's power. Okay? So now, let's see what's going on here. What is this first term going to clean up to be? 1, but I'm going to leave the x to the 0 there to help me figure out what the pattern's going to be. What's going to happen to the next term? It's going to be 0. It's going to be gone. Totally gone. So we're going to mark it out. And the next term is minus 1 over 2 factorial, and leave the factorial there if it doesn't reduce, x squared. Next term, gone. Next term, plus 1 over 4 factorial x to the fourth. Last term, gone. Okay. Now, 3 terms, sometimes 4 is usually enough to see the pattern. But we had to go out 5 in order to get enough terms left over after all the ones canceled out. Okay? So, I recommend starting at 0. Okay, I just do. Most of the time, starting at 0 is good. You may have to adjust as you go through this. First thing you look for, is this series alternating? Is it alternating? Yes. And because I have fractions in it, I'm going to go ahead and put a fraction bar. I'm going to put a negative 1 to the top and put a power of n on it. I'm going to guess at first that my power should be n. If using n doesn't work for the first term, I'm going to change it to an n plus 1. So here's what I do. Plug 0 in for n. Will that give me the correct sign for the first term?
No.
Negative 1 to the 0 power is 1, which is positive, and that's what I want. So that's good. That takes care of the alternating. Okay? If you take the alternating out of the picture, what are all the numerators?
N factorial. Oh.
The numerators. They're all 1s. So I don't need to do anything else to the top of this thing. Do you agree with that? Now, I'm going to go ahead and put the 0 factorial back on the bottom of that. Okay? What is the pattern for the bottom? It is 2n factorial. Do you see that I'm doubling every time? Okay? If you look at just the numbers themselves, I'm adding 2 every time. And like we talked about at the beginning of class, when you add 2 every time, it's 2n, right? So we're going to put parentheses 2n factorial. That takes care of the n's. Yes, ma'am?
So that doesn't affect how the negative goes to factorial? Because you said b plus 2, but that plus 0 to negative 2.
Okay, if I plug a 0 in here, that's still going to give me a positive 1. But if I plug a 0 in here, that's going to give me 0 factorial for the first term. The next thing I plug in is always a 1. If I plug a 1 in here, negative 1 to the first is negative 1. You see it? And then the bottom will be 2 factorial. Okay, what have I not talked about yet? The x. Okay? So out to the side, I always like the x out to the side. What is x's power going to be? It's 2n again, because I'm going 0, then 2, then 4. So this is x to the 2n, and there's your pattern. That, I believe, is the hardest thing about this lesson, is finding the pattern of the numbers. Because everything else we've done before. This is the really only new thing. So what we're going to do is we're going to put plus dot 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 plus what we just found, negative 1 to the n over 2n factorial x to the 2n plus dot dot dot. Now we have created the series. Series has to have the dot 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 at the end to show that it's infinite, and it has the nth term in the middle. Okay, so now I have generated the Maclauren series for this. But now we need to figure out the interval and the radius of convergence like we did yesterday. Okay? So, what we did yesterday is we take what's inside and we do a test to it. Specifically to the end stuff. What test should we use for this process? What do you think we should use? Ratio test, because why? Because of the factorial. So, this doesn't leave me a whole lot of room, so I'm going to have to squeeze it in over here. So we're going to do the ratio test. And I'm going to write that down. Ratio test. This is going to be the limit as n approaches infinity of... Now, when you do the ratio test to an alternating series, you really, because of the x's involved, you need to keep the negative 1 in there. So we're going to have, where am I? Negative 1 to the n plus 1 over, or let's go ahead and make it all into one fraction this time, x to the 2 parentheses n plus 1 over 2 parentheses n plus 1 factorial. I'm going to go ahead and say this on camera just to make a comment about it. On the power series lecture, I did make a mistake on one of the problems. I had a 2n and I just added 1 to the end when we did the ratio test on one of the problems. And I realized it after I was editing the video. Now, the answer came out to be exactly the same, so it didn't affect the final result. But you've got to remember that if a 2n is involved, it's not just 2n plus 1. It's the n is being replaced with n plus 1. So when I distribute this right here, what's it going to turn out to be actually? 2n plus 2. Okay? And we're going to do it correctly this time to make sure that it's working right. So now I got to put my big fraction bar and put the original on the bottom. So it's going to be negative 1 to the n x squared, x to the 2n, excuse me, over 2n factorial. Draw my line. Now what I'm going to do is distribute and flip all at the same time. So this will be the limit as n approaches infinity of negative 1 to the n plus 1 x to the 2n plus 2, like we just said a minute ago, over 2n plus 2 factorial times, scoot this over, make sure we get it all in the picture. Take the bottom one and flip it. So this is 2n factorial, negative 1 to the n, x to the 2n. Close my absolute value. Does everybody understand where everything came from? Are we all good with that? Yes? Okay. Let's talk about the negative ones first. If I reduce that, what will I have and where will it be? Negative 1 on top. So I'm going to do this, marks this out, leaves a negative 1 up there. Okay. Let's do the x's next because they're the next easiest one to do. If I mark out the x's, how many are left and where? X squared on top. Does everybody understand why it's x squared?
No.
Okay. Remember that this is the same thing as x to the 2n times x to the 2. Right? Because when you add exponents, they came from multiplication. Do you see that? So now what happens is the x to the 2n cancels the x to the 2n at the bottom, leaving the x squared. Another way to think of it is how many higher is the top than the bottom? It's 2 more x's, So it's like an x times an x, which is an x squared. Okay? Now, as far as this goes, you can't just cancel these two and just say it's 2 factorial. It doesn't work that way. What we have to do, first of all, which one is bigger? The bottom one. We take the bottom one and we start writing it out factorial-wise until we get it to match the top so we can cross them out. Okay? So we start with 2n plus 2, because that's where we are. What's the next one down from that? 2n plus 1. And what's the one down from that? 2n. Now I match the other one. So throw a factorial on that one. Mark out the one that I just broke apart. And now the 2n factorials cancel, leaving me those 2 parentheses on the bottom. Are you in agreement? Yeah. Okay, so let's write down what's left. So we have the limit as n approaches infinity of, what do I have left? I have negative 1x squared on top over 2n plus 2 times 2n plus 1. Agreed? That's all that's left. Okay. Now, remember we're doing the limit that affects n. So for the moment, we're going to treat x as if it's not there. You can plug in a 1 for x in your mind if you want to. Cover it up with your thumb, whatever works best for you. What is that limit going to be with just the ends? 0. 0, because it has ends on the bottom. It's 1 over infinity. So this, now, does x even affect that?
No.
If the ends all make 0, 0 times whatever x is doesn't matter. It's still going to end up with an answer of 0. Okay? So this equals 0 no matter what x is. Agreed? X could be 1,000,000 and it's still going to be 0. Now, what has to happen for a ratio test to converge? Absolute value has to be less than 1. Is mine less than 1?
Yeah.
Yes. So I'm going to write this is less than 1. Therefore, I'll kind of draw a little line here. This one converges for all x. It doesn't matter what x is, it's going to converge because it's always going to be 0. Are you with me on that? Okay. If it converges for all x, that means the interval is what to what? Negative infinity to infinity. Exactly. Now, using Olu's method, I'm going to call it a method because it's actually a formula. What's r? What's infinity minus negative infinity divided by 2? Infinity. Exactly. So there is the answer for the interval of convergence. Questions? Now, yes?
Why does it converge for all x's again? You said because because it's always going to be x when 0 is less than 1.
Okay, what I said was this. When x is taken out of the picture, that limit is 0. So if I bring x back into the picture, if all of that equals 0, it doesn't matter what x is. It's still going to be 0. And since it's 0, and 0 happens to be less than 1, which is what needs to happen for it to converge, it's going to converge for everything. Okay? Question?
What's R?
What is r? R is the radius of convergence. Basically, when we're going to do another problem in a minute, that once we find out how far apart it is, it's the distance from the center to the ends of the interval of convergence. Okay? Any other questions? Are we good? Okay, let's do one that's not infinite. Let's look at number 2. We're going to get a start on this before we have to change. Yes, sir?
So, this doesn't relate to the question really, but is infinity minus infinity 0?
Nope, it's not necessarily, because infinity is not a defined place. One infinity could be 1,000,000,000,000, the other one could be 1,000,000,000. Do you see what I'm saying? Yeah, they are not necessarily the same.
What about infinity over infinity?
Infinity over infinity could be anything. That's a keep going, like 0 over 0. That's why we do with L'Hopital's rule, that's why we do keep going, because we don't know what it is. All right, so now let's look at number 2. Use the function f of x equals 1 over x to find the Taylor series centered at 1. So that means that c equals 1. C didn't matter in the last problem because it was negative infinity to infinity. But it will in this one. It's going to matter. All right. So 1 over x, to take its derivative, I don't want to do it like that. That's Lodi high. I want to change it to an exponent. It's x to the what power? Negative 1. Okay? Now, I'm going to try and see if you guys can follow along with me, and we can go ahead and put it back into the fraction and take the derivative that way every time. Okay? What's the derivative of this going to be? Negative 1 x to the negative 2. So it's going to be a negative 1 over x squared. Do you agree with that? Okay? Now, remember that that x has a negative exponent. So when you bring it down for the next derivative, what's it going to be? Positive 2, that's your new numerator, over x to the third. Yes?
Can we just write it how you did the first one?
You can, but plugging in the 1's going to be a lot easier if you do it this way. If you want to write it that way and then change it, that's fine with me too. Okay, this is 2 and a negative 3. When you multiply 2 and negative 3, what do you get? Negative 6 over x to the fourth. Positive 24 or negative 20? Positive 24 over x to the fifth. And then negative 120 over x to the sixth. Okay. So when I plug in 1, what are the answers always going to be? No. Well, the x's are going to be 1, but what's the answer for each one going to be? It's going to be the numerator, right? So it's going to be 1, negative 1, 2, negative 6, 24, negative 120. Agreed? All right, let's now go ahead and write out the series for this. So I'm going to write the sigma over here. Leave some space to put its stuff in there. And 1 over what for the first term? 0 factorial. X to the, wait a minute, it's not just x. X minus 1 because c is 1, very good. X minus 1 to the 0. Plus negative 1 over 1 factorial, x minus 1 to the first. Plus 2 over 2 factorial, x minus 1 squared. Plus, do you think you could do the rest? Mm-hmm. Do the rest. What's the first coefficient going to be?
1.
It's just 1. And I'm going to go ahead and leave the x minus 0 there, because it helps to figure out how to do the
Wait, is it x minus 0? Or
x minus 1. Thank you. Good catch. Next term. Negative 1, x minus 1 to the first. Agreed? Plus, now, do you notice anything about the fractions that are coming up?
They are equal. The top and bottom are the same.
This top and bottom are the same value.
Yes.
Think about it. Isn't 6 the same thing as 3 factorial? Isn't 24 the same thing as 4 factorial? Yes.
Yeah.
Now, in this one instance, since they do reduce to a single term, we want to go ahead and get rid of the factorials. Okay? If it doesn't reduce, don't reduce it. But now I know that this is going to be 1 x minus 1 squared. Now somebody else mentioned that it's alternating, and that is true. We're going to need that later. So I'm going to go one more. The next one's 1 x minus 1 to the third plus dot, dot, dot. I'm not going to do the last two because I already see the pattern. Go out about 3 at minimum. And if you see the pattern with 3, stop. Okay? Now we got to go back and build the sigma. Okay. First thing we looked at before, do you remember what that was? Pardon me? Yes, we're going to figure out what the n is. But the first thing I did on the last problem was the alternating. Okay? Does this thing alternate?
Mm-hmm.
Yes. So there is no fraction though, so I don't need a fraction bar. I just need to go ahead and put the negative 1 in there. And an nth power. Does that work to create the correct sequence, plus, minus, plus, minus? If I start at 0. If I start at 0, does that work? And the answer is yes, because -1 to the 0 is a positive. All right? So that takes care of all the ones. What is the rest of my series going to be? X minus 1 to the n. Exactly. There it is. I built it. So come over here and put it on the end of what you just did. -1 to the n, x minus 1 to the n plus ... And we have now built our series. Okay? Does everybody see that? Now, that one wasn't too difficult. All right. Now, we need to test for convergence. So what test would you like to use based on this formula right here? I would say root test, because they're both to the power of n, right? Root test is easier than ratio as far as the amount of work that's involved. So if you can use it, I'd suggest you do. So root test, here we go. This is limit as n approaches infinity. Now before I put this in here, I'm going to go ahead and put both terms in a single power of n. All right? So that means it's going to be a parentheses, -1, and then x minus 1 to the nth power inside the absolute values, 1 over n outside the absolute values. Did everybody follow what I did with the nth power? All right, what's going to happen to the powers? They go away. It becomes 1. Okay? And I no longer need the limit because there are no n's left. So I can just take what this is, which is -x plus 1, close it off. That's what it reduces down to. That's all that's left. Now, what does that expression have to be in order to converge?
Less than 0.
Not less than 0.
1.
Less than 1. Less than 1. Okay. Now, we did this yesterday. How did we tackle situations where we have an absolute value? Go for it.
You make it between -1 and 1.
Make it between.
And drop the bars.
Right. So we do -1 is less than -x plus 1 is less than 1. That's what the absolute value means.
-1, both sides.
And we're going to subtract. Okay, what I recommend you do, this is a review for those who weren't here, cover up one of these. This is called a compound inequality, by the way. You cover up 1/2 of it and just look at the middle. What do you need to do to solve for x? We need to subtract 1. So we're going to subtract 1 here and here and here. All 3 places at once. So -2 is less than -x is less than 0. Now, how do we get the x by itself? Divide by -1. And what happens when you divide by -1? You change the inequalities to the other direction. 2 is greater than x is greater than 0. And so there is my interval. Interval of convergence is 0 to 2. No brackets, no parentheses yet. Question?
So the absolute value doesn't actually affect what's inside? Like it doesn't change the -x to +x?
No, because the terms haven't been combined yet. They act like a parentheses. And what has to be done in the parentheses has to be done first. All right. So why did I put 0 to 2 with no brackets or parentheses? Because I have to test the endpoints and see what's going to happen. So at x equals 0, ... That means we go back to the nth term that we created, either here or over here, and we plug in 0 for x. So that means this will be -1 to the n and -1 to the n again. Did y'all follow that? And if you put them into the same parentheses with the same n, that's going to clean up to be +1 to the n. Do you agree with that? So write out the series to know whether it converges or diverges. We started at 0. So if you plug in 0, what do you get? 1. If you plug in 1,
1,
plug in 2,
1,
plug in 3, ...
1.
Converge or diverge? The whole, okay, the sequence is going to always stay 1, but if you add them all up, is it ever going to get close to a number? No, it's just going to keep blowing up big. So this diverges. That diverges. Okay? Because it diverges, does 0 get a bracket or a parentheses? It gets a parentheses because it's not included. Because convergence means it works.
Yeah, I was thinking of parentheses, but I said bracket.
Okay, okay. All right, now we do the same thing to the 2. X equals 2. Go back to the problem. You still see it? Yes. Negative 1 to the n. 2 minus 1 is 1 to the n. And negative 1 times 1 is negative 1 to the n. So, some of you will know immediately what that's going to do. Some of you will need to write the terms out. I'm going to go ahead and write the terms out. So plugging in 0 first is a 1. Plugging in 1 would be what? Negative 1. 2, positive 1. 3, and so on. Converge or diverge? Why? It oscillates. This thing oscillates.
When it oscillates, doesn't that mean it diverges?
Yes. It oscillates, therefore it diverges. Okay? Now, just to be sure that everybody understands, oscillate is not changing signs alone. Alternating means changing sign. Oscillating means changing sign, and the numbers always go to the same term each time. Oscillate has to go up and down the same amount every time. Yes, ma'am?
Since it's, why is it not like converging to 0? Because they cancel out.
They do cancel out, but once you stop, you don't know where you're going to stop. Do you see what I'm saying? When you converge, the sum of the things have to, no matter where you stop, be very, very close to 0. If I stopped with a positive, it would be stopping at 1. If I stopped with a negative, it would be at 0. That's the difference. Okay? So does 2 get a bracket or parentheses? 2 gets a parentheses. And now, one more thing I need to do. I didn't leave myself a whole lot of room. Figure out what R is. And we're going to use Olu's method to do this. For those who did not catch this yesterday, it is taking the second term, the two interval ends, subtract them, divide by 2. 2 minus 0 is 2, divided by 2 is 1. And I had a thought during first period today. You know what this looks like? B minus A over N. Think about it. If you think of this as an A and a B, it's a B minus A over N. It's finding our radius. Did you have a question?
Oh, I was just wondering, like, do we have to find R, like, even when they don't ask for it in the,
I would say that's a smart idea to go ahead and do it. Most of the AP questions I've seen have asked you for both. So might as well just get in the habit. So here is the answer for the radius and interval of convergence, and the formula is over here. Okay, questions? Anybody else? Okay, now let's look at number 3. Number 3 says find the Taylor series about x equals 2. This, however, is the first time we've done a Taylor series for a polynomial. Okay, and something unusual is going to happen with this when we do it. Okay? So I'm going to do this one a little bit differently. I'm going to do it, I did it out across the page last time. It took up so much paper. So I'm going to do it kind of in the tabular form that they did it. So F, and then F prime, F double prime, F triple prime, F to the 4th, and I want you to go to the 5th for a reason. Okay, go ahead and under F of X copy down the original problem. Okay, now I'm going to give you a minute or two. I want you to take the derivative over and over again until you get to the bottom of the list. So we're centering at 2. F of 2. So let's do some mental math. 2 to the 4th is what? 16 minus 2 to the 3rd is 8. 16 minus 8 is 8. Minus 4. 4 plus 2? 6. Okay, 2 in the next one. 2 to the 3rd is 8 times 4 is 32. 2 squared is 4 minus 3 is 12. What's 32 minus 12? 20 minus 4 more, 16. Okay, double prime. gets a little bit easier. 4 times 12 is 48. Minus 12. 36 minus 2 is 34. 24, 2 is 48. Minus 6 is 42. What's the next one going to be? 24. You can't plug anything in. And what's the next one going to be? 0. Okay, now if we build this thing, we're going to end up with the 6. Oops, I better move over. I'm not going to have enough room if I don't. So I'm going to draw a line right there. So 6 over 0 factorial x minus 2 to the 0 plus 16 over 1 factorial x minus 2 to the first plus 34 over 2 factorial x minus 2 squared plus 42 over 3 factorial x minus 2 cubed plus 24 over 4 factorial x minus 2 to the fourth plus 0 over 5 factorial x minus 2 to the fifth. Now, I wrote that for a reason. Oh, you can't see it. The invisible line. What is going to happen to that last term? It's going to go away. Just like, remember when we did the cosine one where every other term went away? This one's going to go away too. Okay? If I did a sixth derivative, what would happen? The sixth derivative would be 0 also, and so would the 7th, and the 8th, and the 9th, and the 10th. So unlike all the others, there is no pattern beyond 4, and it stops. Okay? That's because it's a polynomial. Polynomials always stop. All the weird ones, all the transcendentals, the e's, the logs, the sines, the cosines, they keep going. But this polynomials don't. Okay, so let's just clean this up, and we're done. Because there's no nth term defined. There is no nth term pattern. First term is just going to be 6. Agreed? Plus 16 over 1 factorial is 16, x minus 2. What is 34 divided by 2 factorial? 17, x minus 2 squared, plus, now 3 factorial is 6. That's going to be 7, x minus 2 cubed. What is 4 factorial? 4 factorial is 24 divided by 4 is 1, x minus 2 to the fourth. And we're done. That's the answer. That is the Taylor series for that polynomial about x equals 2. Okay? Now, the only kind of polynomials that if you take the derivative, the only kind of functions that if you take the derivative multiple times and you eventually get to 0 are polynomials. Everything else goes in cycles. E goes in cycles, cosine goes in cycles, etc. This one stops. Now, here's the weird thing. If I took and I multiplied all this out, multiplied all that out, squared that, multiplied by 17, I'm not going to, cube that, multiplied by 7, what do you think it would end up making? The original problem. It would make the original problem. Okay? All we did was rewrite the original problem in a new way, centering it around 2. Okay? Now what happens is, I'm not exactly sure, my memory, I'd have to do some more research. I'm not exactly sure why you would want to do this in the first place, honestly. Okay? But I will say this, if you needed to find the functional value of this at 2.1, okay? If you put 2.1 in this parentheses, what would the parentheses become? 0.1. 0.1 squared is just 0.01, right? 0.1 cubed is just 0.001, which is an easy thing to do to each of those numbers. Mathematically, if you were doing a 0.1 in there for x, it would be much quicker to do it here than it would up there. Why? Because 0.1 to a power is just moving the decimal one more place to the left.
Right, but in like the ones in the above.
2.1 to the fourth, you would have to multiply 2.1 times 2.1 times 2.1 times 2.1.
Oh,
See what I'm saying?
Okay.
And then add to it the next one. Yeah, it just gets to be ugly. So, anyway, that's what's happening here. The point of doing this problem is to show you that it's eventually going to stop. Okay? So, any questions? Yes, sir.
So when we were putting R, you were saying Euler's method, right?
Euler's method. He came up with it.
You were saying Euler's method.
I was saying Euler's method, yes. We were trying to come up with a formula to figure out R yesterday, and that's what we did. All right? Any other questions? All right, very good.